Nice. Okay, Tuesday. Let's see. Tuesday, lab 11. Yeah, lab 11. All right, let's get right into it. So let's just go briefly through the PDF and kind of orient ourselves with what's going on here. Let's share screen. One second while I send up my drawing pad. Okay, we're online. So there's 3 parts to this, and what I did for my previous lab was this. We can give solutions to a half of the problems here, and there's like 6 problems technically. There's like three problems, and then each of those is 2 parts. What I'm thinking about doing is this. I'm going to give solutions to solutions. That's a bad color. That's a gray background. Solutions to 1.1, 1.2, and 3.2. So that's going to be the differentiation and the partial differentiation problems, and then 3.2 is like Simpson's integration. So those 3 I found to be the most funky, and then 2.2 I can show the skeleton code for like how to do like the different Lagrange. No, it's like Riemann, Simpson, and trapezoidal. Those rules. But full solutions to those 3. Are there any objections to that? Because I feel that 2.1, 2.2 to an extent, and 2.3 are very straightforward. No, not 2.3, 3.1. 3.1 is literally 1 line, by the way. I'll give like 10 seconds for any thoughts on that. Okay. See a thumbs up. Okay, let's start with number 1 then. We'll go through the whole PDF just very briefly. Helicopter speed, we have a number line, let's say, and then we have a car traveling along that number line. Let's say we have 1, we have 2, we have 3. And we know the x and the t at each of those points, xt, xt. We know where the landmark is. Imagine these are like a radar tracking station or whatever, and it tracks the car's the time at which it passes that point. And based on those times, we'll be able to get number 1, speed, and 2, acceleration as it passes each of those landmarks. It'll be an estimation, but because we don't actually measure the speed or acceleration at that point, we're going to need to kind of interpolate. We'll estimate, I should say. So there's a few things that we should be aware of here. First of all, the output units, we can get it in miles per hour or feet per second. And depending on which of those is true, we'll need to do a conversion. And yeah, there's going to be 3 methods we're going to use. For most of the points, we're going to use something called central difference method. So let's say I want information at 2 over here. That means I'm going to want to take we're going to do like position at 3 minus position at 1 over time at 3 minus time at 1. So that's going to be the central difference method. Like you take like the left and right of those to estimate the middle. Now, obviously, you can't really do that for the edge points because there's no, like, one of those is going to be out of bounds. So we'll need to use like forward and backwards difference method for those. And you'll see what those look like as we go along. That's the first one. Clear this. That's 1.1. And assuming I didn't miss anything else. No, this is just an alternate method. Okay, this one is probably the hardest, or at least the most complicated one, in my opinion, out of the entire set. It's partial differentiation. So what we're going to do is we have like a grid of xy coordinates. Let's say 1, 2, 3. Basically, we have two number lines, 1, 2, 3. And at each of those points, we're going to try and generate a vector of partial differentiation. Now, if you guys remember the quiver plot from a couple labs back, like each of these, we're going to basically make a slope field. Something like this. And it's going to point in the direction of greatest increase. That's what the gradient basically means physically. And we'll need the partial derivatives of whatever function we're given. We don't know it is exactly this function. We're given some function. But whatever our function is, we're taking, what this means is partial of our function with respect to this variable x. That means treat x as the variable and everything else as a constant. Let's kind of do a little bit of practice here. So let's say we have like f of x, y, z, alpha. We have like a function of a bunch of stuff. And that's like x, y, z, alpha. If we want to take the partial of, let's say, f with respect to alpha, then that's just going to be, oh, take this as the constant. Pretend this is our x per se. Everything else is a constant. Everything else is like 2 or 3 or 5 or pi. So we'll just do x, y, z. This is like a constant. And then alpha by the power rule just disappears. Or I guess it becomes alpha to the power of 0 or 1. So that's a brief introduction to what you will do or have done possibly in Math 53. Or whatever your equivalent of multivariable calculus is. So yeah, this is just some more examples of how to take the gradients of various, it can get a little bit ugly. Well, here's the central difference of formula, first of all, like in the general case, like no matter what function you're given. And yeah. Clear this in 3, 2, 1. There we go. So we're given a function. It could be sine, it could be cosine, it could be sine times cosine plus 2 to the power of something else. We're given a set of bounds, so we'll have this basically defines a square or a box, bounding box, like this. Like here's your left bound, right bound, bottom bound, top bound. And n is the number of grid points we're going to chop this into. So like chop, 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 n high, n long. Same number of grid points in each direction. And then the double array, this is just going to be an array that, okay, here's something you may not have seen before. This is a 3-dimensional array, but don't be scared. All it is, it's basically kind of, imagine this as like a cell array of 2, like n-2 by n-2 matrices. It's like we're like stacking them on top of each other. This represents the partials with respect to x, and this one represents the partials with respect to y. And you'll see it's n-2. That's just because we're doing some shenanigans with the central difference method. So like we're only evaluating the partials at the points where the central difference methods can be applied. Kind of think back to like the first part of problem 1 if you have kind of conceptual questions about that. Let's see. Anything else I missed? Applications. Yeah, we're leaving the edge points alone here. So just the central difference method. We're not dealing with like the edge cases. And contour. Okay, that's it for 1.2. We'll go through all these in detail. So stop share for this one. Oh, not stop share. Whoops. Meant to clear drawings. Okay. So 2.1, I'm just going to show skeleton code for, but I believe it's pretty straightforward. You're given, I believe it's just a normal curve, but they call it Gaussian. and basically integrate the Gaussian using what strategy? Okay, Riemann integral. So use Riemann to calculate, say, from -2 to +2. And it'll always be the same on either side. So I believe they're using like either left or right. I mean, it doesn't really matter whether you're using left endpoint or right endpoint. It should output the same thing. Where does it tell you that, I wonder? Whatever, just use a left or right endpoint, I guess. Okay. Corrugated sheets. So 2.2 kind of builds on that. You're using different methods. There's the Riemann. Let me just write it out. Or no, okay, listen here. So trapezoidal rule, Simpson's rule, Riemann integral. And you're kind of comparing them to see which one is the best. So this is what you're basically integrating over. And yeah, it says here, chapter 18 has an example of kind of how to do this process. Simpson's rule. First of all, 3.1, you can do this in one line. It's just you take this function, like I equals blah, 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 and then you program this. It's like that transcription thing you did in like lab 0 or lab 1. One line. Okay, for Simpson's rule, the idea behind this is you're trying to approximate the integral like this. Here's how you do Simpsons. You have like a really squiggly function like this. And what we're doing is we're going to break this up into n segments. Let's say like n's 4, n equals 4. And what we're going to do is we're going to approximate each of these chunks, each of these, I guess we call them rectangles. So first of all, we're going to try and approximate like this area and this area and this area. You get the point. And we're going to do that by, instead of just graphing this entire thing, we're going to split it up into parabolas. Here's a parabola. Take the area underneath that parabola. Here's another parabola, another one. And the way we're going to get these parabolas is we're going to take like this point, this midpoint, and then these two endpoints. And then we're going to get a parabola that passes through all of these points. That's the idea. Now, you may have seen this before. This is the Lagrange polynomial interpolation from the previous lab. So this one's going to ask you to redo, well, or I guess just copy over the my-Lagrange functions file from your last lab. So if you're confident that that one's correct, then you can do that, or you can like review my older video from last week. So yeah, just make sure that Lagrange works before tackling Simpson's rule. Let's see if I missed anything. Okay, and submission guidelines. Yeah, one more thing. Make sure your my-Lagrange is inside your submission. Very important. I don't want there to be any problems regarding that not being part of your submission. So remember that. My-Lagrange should be submitted with everything that is listed here with your final submission. Okay. Now that was that's all of them. I think we're making good time. Any questions so far? Oh, I mean, I guess there's some in the chat, but let me take a look at that. I haven't been keeping up.
That's just me.
Okay. You've been on top of stuff. Thanks, Nikolai. All right, now that we've gone through the PDF, let's go over to MATLAB. And let's see, I remember to, yeah, skeleton code. Where's MATLAB? Here we go. Let's do that last. Let's start with 1.1. Speed, not sure what the FD stands for. Speed, whatever. Okay, let's do this first. First of all, string comp I, you may have seen string comparison. String comparison I means string comparison case insensitive. So that means this could be capital MPH, lowercase MPH, doesn't matter. So, I mean, if it works, I think that someone said in my last lab that the string comparison just regular without case insensitive, that works for all the test cases, in which case, go ahead. But this is just the way they did it. Now, if it's, so x and t are given in feet per second. So we're going to, if this is mph, we're going to need to do some comparisons. How many feet are in a mile? Can someone tell me?
5280.
5280. Right in the money. Now, how about seconds to hours?
One hour 3600.
3600, yeah. Yeah, 60 times 60. Or if you prefer 6 times 6 times 10 times 10 times. So 36 times 100. If you're ever multiplying like big numbers like that in your head, consider like breaking those up into smaller chunks that you can multiply and then cram those together. Number of elements in X, last index. Yeah, I'll leave this to you to think about why we need to do this instead of just like using like end here. But here's the idea. This is the first, for the first point, we'll need the forward difference. For the last point, we'll need the backward difference. And everything in the middle, we can use central difference. Ideally, we want to use central difference for everything. But yeah, we can't just based on indexing. Okay, forward difference. Now, what is this? We have a number line, 1, 2, 3. Apologize for using yellow. Now we have x2 time 2, x1 time 1. Now we want the speed at 1. And we can approximate that by using it. If you think about it, like dx over dt, aka the speed, is like a slope. Well, it is a slope, actually. It's a slope of, we'll approximate it as like x2 minus x1 time 2 minus time 1. So this is going to be x2 minus x1. Make sure I put a parenthesis so I'm not just dividing the x1. All of that divided by time 2 minus time 1. Let me just check the solutions to make sure that's accurate. x2 minus x1, 2 minus 2. Yeah, okay. All right. Now, for the central difference, since there's a lot of points, we'll just loop over all of them. So from the second index to the second to last index. So last index minus 1. So speed at position, let's say 2, we're going to want to take the right minus the left. That's the central difference method. To find 2, we take 3 minus, well, the right, basically I plus 1 subtracted from I minus 1. This should be a t. Apologies for the delay, but I want to make this clear. Okay. So let's see what we want to do here. So we want to take x at the position to the right, I plus 1, minus the position at the left, I minus 1. All of that parentheses. Make sure to add the one at the start as well. Divide all of that. Let me kind of space this out for readability purposes. Space, space. And all of that divided by, instead of 2 minus 1, I'm going to do I plus 1, I minus 1. Make sure those match up. I plus 1, I plus 1, I minus 1. Okay. And the backward difference. Similar structure over here. We'll do x end minus x end minus 1. Yeah, simple enough for the first part. The second part isn't too different. Time end. Did I miss a parentheses over here? Yeah, I did. And minus. I guarantee I'm going to make a parentheses mistake somewhere in this lab. So point that out if you see it. If and when it happens. Okay. Now for the acceleration, so we have our dx. Dx is speed. So speed is dx over dt. Now acceleration is the second derivative. So I'll write d over dt of dx dt. The second time derivative of x. So it is like feet per second per second. If you look at like the acceleration due to gravity, it's got units of distance over time squared. So acceleration, we're not going to use x for this one because we're going to want to take the derivative of the derivative. In other words, the derivative of speed. So we can approximate that by, instead of saying x2 minus x1 time 2 minus time 1, the indices don't change. What does change is the fact that we're using speed instead of x. Let me erase part of this so we can see that. And that the rest of that's going to be the same. It's just instead of x, we have speed, also known as x dot or dx over dt. Boom. Speed. Speed. Now for the last one, something special happens. It's exactly the same thing. Wait. No, sorry, I didn't want to copy this one. There we go. So in fact, nothing special happens. It's just speed. All right. Did I miss a parentheses anywhere? Not here, not here. Not here. Okay. All right, I think I got everything. Let's head over to the Lab 11 tester and see if this works out. Some stuff in the way. I can't see the side. Here, I'm going to clear this, actually. 3, 2, 1. Okay. Correct result is, now let me run this again. It's kind of stretched out because of the, is that right? 10, looks right to me. Okay, works for me. Okay, let's, any questions so far before I go on to my gradient? I'll let this display for 10 seconds. What's up?
Yeah, I had a question. So wait, so I was wondering, why didn't you do like the first test case and like the last test case for speed outside of like the for loop, or is that just to show us like for an example, or is there like a specific reason for that?
What do you mean?
Like speed 1 and like speed last index, like why are those outside the loop? I mean, I know the loop doesn't catch them, but like, could you have included them inside? Or
no, because let's say I did this from like 1 to last index minus 1 and then scooted this inside the for loop. Look at what happens. We're doing I plus 1, so that's 2, that's fine. But then when you I minus 1, and that lands us at x0.
Oh, okay, I see what you're saying.
We would like to do central difference method if we want, if we could, but unfortunately for the endpoints, that doesn't work. So that's why we need to make special cases for the forward and backwards difference.
Okay, that makes a lot of sense. Thanks.
Yeah, good question. Okay, I'm gonna move on to my gradient. You can type any further questions in the chat. My gradient. Okay, what you're seeing here is like the end result of a very long process of tidying this whole thing up. Like this is a lot uglier before. Basically my gradient, as you recall, is that we're trying to get like this big old quiver plot. But let's just go through it like little by little so we're not overwhelmed. My gradient. First of all, I want to do no, let's do it the way they're drawing it. So x data is like lin space. So like this is the x min, x max. Y data is y min, y max. So here's y, here's x. Let me write y up here. Okay, and this is going to form a box. yay wide, yay tall. This function extends forever in like the x and y directions, but we're only considering the box inside b box. Okay. Setting up the partial derivative arrays, you might be wondering why there's like an n minus 2 here instead of, oh, why isn't it just like n. Well, we're doing something a little bit different for this problem compared to speed FD, which is we're only considering the points where central difference method applies. So let's say we're doing like x partial. Like x partial is kind of like the x derivative. Well, it is a type of derivative, it's a partial derivative, but if you recall from the last problem, it's like, let me go back to it actually. This one over here, you see where we did like last index minus 1 to the last index? Well, this is kind of like that. We're only considering the points that are like 1 away from the bounds. So like, we're only considering like 2 to n minus 1. So like this is like the 2 and minus 1. So because for those points, oh, I want to find the partial derivative of x with respect, like at this point. So I'll take this point, and I'll kind of draw a line between those and use that to approximate the partial derivative at that point. So what we're going to end up with is we're going to have like partial derivative here, 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 here. We're not going to have it at the edges though, because we're not considering the edge points. So that's kind of why, okay, what we're doing is we're kind of squeezing the information inwards in the x direction and then inwards in the y direction. X partial has like a zeros and yeah, so that's going to be, instead of like having an n by n, like here's n, this is going to be like n minus 2, and then we're going to like x these parts out. And then in the y direction, we're going to do the opposite. We're going to compress it in the y direction. N minus 2, n. And then we x this part out. That may make sense once we get further into the code. Okay, that's the x partial, y partial. So from there, and we're going to tidy this code up as well if we have time. I think we'll do this. We'll come back. We'll go through the rest of the skeleton code, and we'll come back to this one. I want to do an exercise. Okay, this is get the partial derivatives and the y derivatives. Maybe I think for readability purposes, I'm going to put these on 2 lines. I'm going to do, so what you're seeing here, this whole mess of a line is f of x comma y minus f of x comma y. So I'll do like dot 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 this. So this is the denominator. So f of x, might as well just write it out, is f of x comma y minus, let me get some more space for myself. F of like x j plus 1 y. And this is kind of what I wanted to tidy up, because the reason we're doing like n plus 1 minus I is we're kind of doing the y in reverse. And the reason is, like, normally when you make a matrix, right, you're going from like top left to like this way, right? You're going down the rows and across the columns. But the way it's kind of like the flip of how we usually graph stuff. When we graph like an XY data, like here's our X data, here's our Y data, and then here's the graph. So it's kind of like it does it this way. Like we're plotting the points like from the bottom left to the top right. So it's kind of the opposite of the way we're kind of setting up this matrix. So what they're doing here is they're kind of like making sure that these directions match up. So they're kind of like taking this and they're flipping it up and down like that. And then that'll get them all this boils down to making sure that our graphs match the matrix. Let me get rid of that. Yeah, that's why that's the end. And if we have time, I'm going to show like a way that I think we'll be able to get the same results with a cleaner setup. A similar thing for y derivatives. I'm going to do like ... and put this on a new line. And these are like the compression, the effects of the compressing it in the x direction and the y direction, respectively. J matches up with x. Yeah. X data, here's the y data. And down here is we're just finding the gradient. We're just taking, we're kind of meshing these together. We have an n by n minus 2 by n for x. And then we have a, no, I did that backwards. We have x derivatives that are like n minus 2. We squeeze it in the horizontal direction. And then we have an n minus 2 in the, well, n minus 2 rows and n columns for the y. And we're doing where they overlap. So they overlap in like the middle n minus 2. This is where they overlap, like here. So all we're saying is we're going to take grad equals this innermost square of x partial and y partial. We're going to stack those on top of each other, kind of like mesh grid. That's, yeah, there's nothing below here. Yeah, that does it. We'll come back to this one and we'll see if we can tidy this up and make it clearer to look at. You can screenshot this now. You can wait till the recording, or you can come back. Yeah, you can screenshot this now, but like this part works. But if you're looking for a cleaner code, we're going to come back to this and then we're going to redo it later once we get through all of this stuff. Any questions so far? If not, I'll go over Gauss integral and the rest of them. Okay, let's go to Gauss integral. Gauss integral, this was the kind of the normal curve you kind of saw in the PDF. Let's do like this. You take a this way, you take a this way, take the integral. And you'll use a Riemann approximation. So you'll divide it up into, I believe it'll look like left endpoint, like that, like so. So once that's accomplished, we're going to add up all those rectangles, Riemann sum, and that'll be our integral approximation of what that looks like. Excuse me. And that's skeleton code. And we'll move on to roof sheet length. So I said I'd show like a little bit of this. Here it is in like code form, but the equations of this are, I believe, in one of the lecture slides. I forget which one it is. Yeah, look through the lecture slides. One of them probably has like what the trapezoidal rule, Simpson's rule, and Riemann are for these. This, by the way, is a left approximation. Though I don't think it should matter whether it's left or right. Okay, moving on to trinomial integral. One line. All you need is one line. It's in the PDF. So I'm not going to give this one as a solution. It would be an insult to your intelligence. All right, let me get this normal curve out of the way. Okay, Simpson's integral. This one's interesting. We want to find what we're going to. Let's see how you want to do this. Okay. We're going to want to find. Let me draw it out. Some function, as I stated before, like that. We're going to subdivide it into n intervals. Let's start at A, we'll end up at B. So our x's are going to be like, let's say we want to take this point and this point and this point and this point and this point. let's use our trusty friend linspace. From A to B, those are our bounds. And the number of points that we want. Okay, we want to have this be like two different. Okay, let's say we're doing like two chunks. This is like a very discretized. Now, yeah, let's do that. So we'll need 3 points like per interval, but some of those are going to overlap. The idea is we'll want to have two, it's kind of like 2n rectangles, but so that's going to be like 2n. This is going to be like 1, 2, 3, 4. So 4 equals 2n. But because we need points bounding each of those, we're going to need one more point than that. So we'll need a total of 5 points. 1, 2, 3, 4, 5. So this over here is going to be 2n plus 1. I equals 0. We're just initializing I because we're going to, this is going to store the sum of all of the rectangles up to that point. So I equals 0. We're going to add on the area of this this rectangle over here. And then the next loop, we're going to add on this one, and this one, and this one. We're going to keep doing that until we finish the loop. So we're going to loop over from 1 to number of elements. Yeah. We're going to start over here at this point, and then we're going to continue until 2. We're going to count. Here's the last one. Second to last, third to last. So we're going to end here. So we're going to do one of these loops for each one of these chunks that we have for each value of n, basically. I believe if we wanted, we could just replace this with every other one. So this could be like, no, let's leave it like this actually. So we're going to do current polynomials, and this is what this is going to do is, remember when I said we're going to take each of these chunks and approximate it as a parabola. My Lagrange is going to give us that parabola, but we need to tell it what to do first. So the inputs of this I'm writing here are x and y, the x and y coordinates. So we have our x. So that's going to be, first of all, we need to tell it what x points to get. So let's see, we want to have the first chunk. We can have x from I. So we'll start from 1, and we need to go to 3. So we'll do I plus 2. That's not a 2. Yeah. Once we do that, we'll have x. So the first 3 points in x. And for this next one, we have a function handle. Yes, we do. So we're going to do f of, I'm going to do this, f of x I colon I plus 2. I keep doing that. Get rid of that one. Okay. So that's the x. One more thing I need to do. I need to do the transpose of this because these need to be column vectors. Let me just make sure that that's what they have. Gauss, roof sheet length, Simpson. I plus 2, I plus 2. Yeah, okay. Now once we have our parabola, we're going to need to calculate the integral of that under that parabola. Trinomial integral is what we defined the previous one. So we didn't discuss that too much here, but basically the inputs are a and b. Now be careful, it's not the same a and b. It's going to be, let's see, we'll need to do the leftmost point, which is going to be xi. This one is going to be xi plus 2. Current polynomials, and that's just going to be what this outputs is the coefficients of whatever parabola we've approximated using my Lagrange. So where P is coefficients, my lag. Okay. That's going to be an approximation. I is going to be some approximated integral. This is a true integral. True means what is this actually equal to if we evaluate and do actual calculus and find out the area under the curve. And once we do that, we can compare the I minus true, the difference between those. I've made a mistake here. What mistake have I made? If I want E to always be positive.
Absolute value.
Absolutely. Okay, is that everything? We could have also done true minus I. It wouldn't matter. Okay, that's all, right? Simpson integral. Well, let's test this out first of all. Let's go over here. I forgot to test out my gradient. I should have done that as well. I tested it out earlier though. It should be fine. Simpson integral, run section. Okay, what did I do? Clear drawings. Okay. Undefined my Lagrange. Okay, well, let's just trust this works. Because I need to like move over the my Lagrange and whatever. Okay. That's the reason why I'm getting this error is because I don't have my Lagrange in my current folder. I need to find that though. Okay, let's just test this one out. 1.2 my gradient. Let's do run section. This is what it should look like in the end. Does that look right? Yeah. Very pretty to look at, but a little bit tedious to set up. That's tendency for all of these quiver plot problems. Okay.
Can you go back to the Simpsons integral one more time?
Sure. Yeah, here we go. Let me expand this out. Okay, you good?
Thank you.
So once again, I'll go through it. Speed FD, this is 1.1. My gradient, Gauss integral, roof sheet length, trinomial integral, and Simpson integral. And you have the tester. Okay. As promised, let's go through my gradient. Any questions so far, by the way, before I kind of do this exercise? Okay. What I'm going to do is this. I don't like looking at this, end plus 1 minus I. What we're essentially doing is this. We're going to change I, right? So 1, 2, 3, 4, 5. And we're going to change that to, like, what this currently does is end plus 1 minus I. So it's going to do, this is going to become 5, 4, 3, 2, 1. What we can do instead, and I believe this will work, is this currently works, by the way. So don't change this if you're skeptical. We're going to test this out. I'm going to do I. It's just going to be I, right? What was this before? N plus 1 minus I. So yeah, this will be n minus 1, n minus 2. Yeah. Let's do this. We'll change this to I. And we're going to change this one to I as well. Nothing else with end, right? Okay. Over here, I'm going to do, well, this is going to start at 2, from 2 to n minus 1. So that's like 2, 3, 4. And n minus 1, that's going to be let me think about this. 2, 3, 4. 4. No. Isn't that like 5, 3? Wait. Here, oh, let me write back. Like, give me like 2 minutes. Sorry, you guys can like, you guys stare at this and like see like what you would do with it. I'm gonna be right back. So let's see. How do I? Okay, give me 2 minutes. I'm gonna do something real quick. Okay, figure it out. So what we're gonna do here is this. This over here. Let me stop annotating. Is like I plus 1. And this over here is going to be I minus 1. Same thing over here, I plus 1. And I minus 1. This will never be out of bounds because it'll be 2 minus 1 as the index here. So what I'm doing here is I'm kind of getting it into the form that's more intuitive to understand. So j plus 1, j minus 1. And y data is always going to stay the same because we're not taking partials with respect to x. So x data, j plus 1, x data, j minus 1. Another fix I'm going to do is I'm going to make this a little bit easier to look at. Let's do it up here, actually. Shift enter. Much better. Y data, shift enter. That's just a little bit more compact to see. And like that. Yeah. That's the same thing, just more compact. Now, but one thing I need to do though, if I'm going to do this, because I flipped the order of these y values over here, I'm going to need to make a small change up here. Now, there's a couple ways I can do this. I could do like flip LR. Flip LR. That's going to flip left, right, and do this. I think that's the most intuitive way to look at it. Another way you could do it is not use this LR and change this to like B box 4 and B box 3. That's the way the tester does it, I believe. But I'm going to do it this way. Flip LR, linspace, B box 3, B box 4. So that's going to make Y from like 1, 2, 3, 4, 5 to 5, 4, 3, 2, 1. And that's going to make this indexing work out. So, and like, there's another change I was thinking of doing is maybe just since we're not ending up using the all of these values. Remember the kind of thing I drew earlier with the x partials being like an n minus by n by n minus 2, and we only use the essential part. We could maybe just do 2 to n minus 1 for both of these. But yeah, let's not, I haven't thought enough about that to confidently make that assessment. Let's just test this out and make sure that it's the same thing. And if so, it'll be less typing on your part. Okay, let's go to the tester and see if this is the same thing. I believe it is, unless I made like a parenthesis mistake somewhere. Let's do, where is it? Oh, what happened? Array indices must be positive integers or logical values. Error in my gradient. Okay, let's do some debugging. Array indices. Okay, so we have a 0 somewhere. Oh, whoops. I had an I minus I instead of I minus 1. Okay, let's try this again. There we go. Let's you can't see the figures, right? I realized I was showing the figures earlier that. Okay, let me reshare that so you can see the figures. Pull the figures. Here's 1, here's 2. Figure 2 is the correct one, figure 1's ours. And I believe those should match up. Beautiful. All right, yeah, do it this way. Less typing, easier to understand. Okay.
Dennis, I'm getting weird errors. It's like showing, can I share my screen with you? I don't know if it's like something that I just screwed up in the code.
Let's just go through, let's do this. Oh wait, for my gradient, right?
Yep.
If you're sharing screen, let's do this. I'm gonna go through the skeleton code and solutions one more time, and then I'll stop the recording, and then I can go to you.
Okay, all right.
Sure. Okay, so once again, speed, my gradient, Gauss integral. So 1.1, 1.2, 1.3. No, 2.1. 2.2, roof sheet length. Trinomial integral, that's 3.1. And lastly, Simpson integral, which is, let me expand this out, 3.2. All right. I'm going to stop the recording. I believe that's Alt-R. I'll just do it manually.